All right, welcome AP. We got 19.5, a beautiful letter called capital G, Gibbs free energy. This is the only one, I started to get a little ahead of myself before I hit the record button. This is the only letter that can tell us if it's thermodynamically favored, aka spontaneous. Not delta S, not delta H. Everyone always thinks that capital S has to do with spontaneous, and it's got nothing to do with it. So only delta G can tell us if it's thermodynamically favored or not. Gibbs free energy change for a chemical process in which all the reactants and products are present in standard state. Now you get a little bit of love here. Remember when delta H, that standard state, all of those values were 0. Sodium as a solid, 0. Cl2 as a gas, 0. Delta S, nothing. No, we couldn't do that for delta S. But for delta G, it has to even be even more specific. So at delta G, standard state, anything in its pure elemental form, but the concentration has to be 1 molarity. So for us to use these appendix values, it has to be at 1 molarity, 1 atm, and our 25 degrees Celsius. We don't use bars in AP Chem, but they always keep bar in there for some reason. I don't know why. So delta G, standard state. So when we're using our appendix, and let me get that guy open. All right, so right here, these delta G values, look at just like how aluminum was. Aluminum as a solid, standard state, 0. Delta G, 0, but not for entropy. Entropy always had a value. Or like, for example, Mr. Cl2 as a gas, 0. 0. Nope, a gas definitely has some disorder, some movement, okay? So when you're looking at delta G, it not only has to be at standard state 1 atm, but it also has to be at 1 molarity. So there's another kind of kicker to this, only when it has to do with delta G. So with this, the standard Gibbs free energy change for a chemical or physical process is a measure of thermodynamically favorability. We want a certain value for that delta G, and that will tell us if it's spontaneous or not. Historically, the term, here comes AP, spontaneous has been used to describe a process when that delta G is less than 0, okay? So thermodynamically favored spontaneous, that delta G has to be negative, not 0, has to be negative. The phrase, here it is, Mr. AP talking to you about that nasty S word. The phrase thermodynamically favored is preferred instead of that common spontaneous. Okay, they don't like it. It's preferred, and it doesn't say you can't use it, but AP don't use it. Okay, because you want to keep them in a happy mood while they're grading. Okay, so the phrase thermodynamically favored is preferred instead of the misunderstanding where students think that spontaneous happens without like a cause or anything like that. You want to avoid stuff like that. So let's just get that nasty S word out of our writing explanation. So we want to make sure that delta G, and I think I just said in my head delta S, but delta G we want less than 0, and that is the only way something will be thermodynamically favored. Okay, that's it. Has to be negative. Okay, and I'm even going to say here not 0 and not positive. Oops, put the word not positive. Standard Gibbs free energy change for physical chemical process can be just like how we've been doing. Products minus reactants, products minus reactants. Nothing's changed, ladies and gentlemen. You got 3 different equations of products minus reactants, okay? Just be very careful with those moles and look at the units, okay? Just like somebody, just like delta H, that kilojoules per mole, okay? So let's do a recap of all 3 of our very new variables that we have done these past 2 chapters. We have delta H, entropy. This tells us about heat transfer. This is the only one you can say anything about endo and exo, okay? Just like, remember if it was constant pressure, there's the heat, okay? So only heat or entropy, you can talk about endo and exo. That's it. Nobody else. Entropy, you can talk about the disorder, the movement. The higher the disorder, the greater that delta S value. Okay, the lower the order, the lower the delta S value, the more the order. So this one's about particle movement. Okay, has nothing to do with spontaneous. Okay, so don't even look at him. Gibbs free energy, here's the one. Is it thermodynamically favored or not? But this is going to be a little new part that we're going to add to it. They want to know if it's thermodynamically favored in the forward reaction, as in A plus B makes C, or is it thermodynamically favored where it's going A plus B this way? We usually call that equilibrium. Okay, so which way is it forward? Which way is it favored? In the forward direction or in the reverse direction? Which one is thermodynamically favored? So for a thermodynamically favored reaction, okay, back in the day when we were doing the beginning of chapter 19, we had delta S universe is the system plus their surroundings, okay? We wanted it to be thermodynamically favored when this value is positive, okay? But hold up. Delta S has nothing to do with telling me if it's thermodynamically favored. This is just what's going to happen if it is thermodynamically favored. So for the delta G, okay, we want a negative value. But in order to get that negative value, how is delta S and delta H going to play into it? So this is the big question, and there's an equation that's going to tie it all in. So usually, for thermodynamically favored, your S value will be positive, okay? For reactions with very large negative delta H's, remember, exothermic is the way to go for that thermodynamically favored. You're going to get a delta H that's negative. So our delta G should be negative, our delta H should be negative, and our entropy should be positive. Now, ladies and gentlemen, that should make sense because the positive delta S is disorder, chaos, okay? We're looking for something probably with a lot of gases on the product side. So this is how all three of them are going to get tied in. But when I ask you the question, is this thermodynamically favored or not, and you're looking at H and S, we've been lost since this recording started. You can only look at G for thermodynamically favored. Just like endo and exo. I saw in the chapter 5 test, you guys were talking about how work was being done on the system or the surroundings. Are you kidding me? Work has nothing to do with endo or exo. Okay, that just makes it either positive or negative for system and surroundings. So there's even more learning targets with this. This is a big one. Explain whether a physical or chemical process is thermodynamically favored based on that delta G, okay? In some cases, it's necessary to consider both entropy and entropy. So, when they're giving you data, if they mention those delta G's, and delta H's, and delta S's, you have to use all three of them to prove that it is thermodynamically favored. And the only way to do that, as you see right here, is these values should be exactly what they should be if it is going to be thermodynamically favored. So this is usually, whatever the values may be, they just have to be negative or positive. This is the preferred thermodynamically favored, okay? So if they give you the H and the S values, you have to use the data to confirm if it's thermodynamically favored, okay? So like the freezing of water, the dissolution of sodium nitrate are examples of that phenomenon. So just like how we did in chapter 5, where you did an equation of Q equals MC delta T, and I think it was like potassium nitrate dissolved in water, and the dissociation was exothermic because it produced, the temperature went up, and that means that your Q was negative. Same thing. So knowing the values of H and S, we now can tie it all together in an equation. And you get this equation on the AP sheet. Just like you get, which I've never understood, why they give us all three equations for products minus reactants, products minus reactants. I don't know. Out of all the equations in the world, that's probably not ones I would put on there as the most important because I think that's not hard to remember. If you have Gibbs free energy, which is capital G, as a state, notice there's no triangle. Okay, so there's no initial, there's no final. That means that all constants, okay, or actually I'm going to say the word, all variables are not changing. Okay, so all variables are not changing. Okay, as in no triangles. Okay, However, ladies and gentlemen, you know we like to change things. That's the whole point of chemistry, physical and chemical processes. Whether it's a chemical change or physical change, doesn't matter because look right here. They said whether a physical or chemical, now we're going to change it. We just don't know if it changes to a new substance. That could just stay physical. So this is the one that you're going to mainly be using. I don't usually use this one because we're doing chemical reactions, which means things are going to be changing. So whether it be a physical or chemical reaction, delta G equals delta H minus T delta S. Units, okay? Well, actually, let me rewind there. Notice who is not changing, okay? That temperature is constant. Okay, and that is key, ladies and gentlemen. Most of the time that temperature will be room temperature. Okay, and I'm just going to put the word most of the time. It's at 25 degrees Celsius, 298 Kelvin, most of the time. If they want to change temperature to a different number, that's fine. Then they'll give you that different number. But it's the units that are going to get a little wonky. Okay, and let me do some little plane of the units right here. Let me do it in a different color. Usually G is kilojoules per mole. We already know delta G, you're going to see a huge correlation with these two values, G and H, big time when I get to 19.6. They go hand in hand. And how do you know that? Because look at what we just did right there. For thermodynamically favored, both of those values better be negative. Okay. What really trips students up, it's the S. Okay. Because remember when we did S, it was joule mole K. This is the big problem. For this delta S to plug into this equation, you have to convert that joule to get it into kilojoules mole K. Don't get freaked out, ladies and gentlemen. It's just King Henry moving it 3 times. That's all it is. But that S right there, you cannot put joules there. You have to convert first and then multiply it by the temperature. Okay, so this right here, this S has to be kilojoules mole times K. Now, ladies and gentlemen, when you multiply that temperature and S, obviously the K's will cancel, and we want it to. Because basic math, when you add and subtract something, they have to be the same unit. Okay, so these two right here, when you subtract, make a little note over here, need to be the same units. Okay, that is basic math law. Okay, so depending on, we're going to do a couple calculations, so have that calculator ready. The sign of delta G is important in predicting the spontaneity, whether it's thermodynamically favored. Use those big words. Make sure you spell them correctly too. That's the one we want. We want delta G to be negative. And that means, it means a lot of things. Delta G negative in the forward direction is thermodynamically favored. And we already know from the second law of thermodynamics, entropy is always increasing for the universe. So this irreversible right here has to do with the second law. Your temperature should be very high. So notice when I say these temperatures up and temperatures low, that means it should be like for a higher temperature. I can't tell you what that number will be, but usually we just think of it more as room temperature. So it just needs to be greater than that room temperature, and that means it should be thermodynamically favored. You're going to also know that your delta H will probably be negative, and why? That's called exothermic, ladies and gentlemen. And we want it to be negative because remember, exothermic was also an indication of thermodynamically favored. Okay, and you will probably see, okay, like I said, the word probably, see the delta H should be positive. Okay. The only time you have reached equilibrium, let's do like a little different colors here, is when that delta G is 0. That's it. It's not favored in the forward. It's not favored in the reverse. It's at equilibrium. There's no change that's happening. If that delta G is positive, then it is not thermodynamically favored in that forward direction. We're always looking at the forward direction, producing those products. Okay. However, if you do reverse it, we just got done talking about a chapter called Hess's Law, where, however, the reverse reaction would make it thermodynamically favored. So if you flip the equation, and you're going to see a video, I think it's the video in AP Classroom, I was just watching it, video 9.6. You're going to see when they flip the equation, the delta G just flips the sign. So they use Hess's law, which you guys did very well with. It's just I got to yell at you on sig figs. The delta G will be just a flip of the sign. So if in one case it's positive, I can get it to be thermodynamically favored when I flip the equation, because now the delta G will be negative, and now that makes it thermodynamically favored. But now which way is it favored? It's now favored in the reverse direction. So the delta G is greater than 0. Work must be usually supplied to the surroundings to get this to drive the reaction. This is very key because that's how W kind of plays into this. Okay, so the work must be supplied from the surroundings, as in going to the system, to drive this reaction. So if your delta G is positive in the forward, that means it will be thermodynamically favored in the reverse. Okay. Thermodynamics always gives us a direction, whether it be forward or reverse. However, it tells us nothing about how fast it goes. That's called kinetics. Okay? And you're going to see I got my AP Classroom kind of near me too. You're going to see an AP video, and it's video 9.4, and you're going to see how they're going to tie in thermodynamics and kinetics. Okay? So good watching there. Okay? Let's practice this. So this right here, I just took an example question. We're going to calculate standard free energy change, which means we're calculating delta G. Sometimes they call it Gibbs free energy. Sometimes they just call it free energy. Okay, do not correlate it with delta E as an internal energy. I know it's all these letters all over the place. Okay, but that's why you're AP. You got to learn it all. Standard, the degree sign. Okay, so that means that standard state is at 1 atm, 25 degrees Celsius, which we see it right there. And they don't usually tell you the 1 atm part because the word standard tells us it all. So they want what's delta H for the formation of, we want to form NO. Okay, I'm just writing always a balanced equation from N2 gas and O2 gas. So I want to form NO from nitrogen gas and oxygen gas at that 298, given that delta H is this and delta S is that. Okay, so that's about all we have to go off with. So let me get set up too. You guys get your calculator. Let's get a little plug and chug going on. As always, let's balance our equation. That is always good. So first, let's calculate that delta G. So we have our equation just sitting right there. No products minus reactants because they want us to use the H and the S. So first, delta G, and use the little degree signs. Delta H minus T delta S. Okay, so I have my delta H, and my delta H was 180.7 kJ. Sometimes they put the mole, sometimes they don't. I'm actually going to put the mole because I got this from an old problem. Oops, put the mole right there. So kilojoules per mole. Now we know the temperature right there. This temperature has to be in Kelvin. I should probably even put that in our equation up here. Okay, make sure, I know all these lines going all over the thing. Temperature has to be in Kelvin. Okay, always, always. 298 is our Kelvin. Okay, now I'm going to use parentheses over here because remember, ladies and gentlemen, these temperature and delta S, they are multiplied by each other. But we need to take this delta S and we need to convert. So 24.7 joules moles K. And remember, ladies and gentlemen, you got joules in the box and you got kilo 3 spots over. Okay, so we should always be moving the decimal 3 places to the left. So this is going to become 0.0247 kJ mole dot K. All right, so hopefully I did not ruin that moving the decimal. We should be going 3 to the left, so 0.0247. And I'm going to be plugging that number right here. Okay, so word to the wise, don't forget to convert units for only this guy. So now I got 0.0247 kJ mole times K. Obviously, my k's are going to cancel when I multiply, but we got to do that part first. So I'm going to take that 298 times 0.0247, and I'm going to get now, I'm sorry, I'm out of room over here, minus 7, and we're multiplying, let's see, 3 sig figs, so 7.36, and now I got kj over mole, because my Kelvin's canceled. But I still have this 180.7 in the front. Now, you guys are killing me with your sig figs lately. Children, we don't have time nor the points to be losing stuff on simple stuff like sig figs. We have to make sure we're following those rules. So adding and subtracting the least after the decimal. So 180.7 minus, that's 7.36. Okay, so my delta G for this reaction, sometimes you'll see the word reaction, you'll get this 173.3 kilojoules per mole. Okay, there it is. All right, so now with this, let's answer some questions. Is the reaction endo or exo? Okay, well, the only value you should be looking at is that delta H. And my delta H was positive. Okay, so it's endothermic since my delta H was positive. There you go, easy peasy. Does the entropy of the system have more disorder or less disorder? So we're looking at delta S. Now my delta S value up here was positive. And what do we know when it's positive? That means I have created more disorder. Okay, I have more particle movement because it's positive. I don't have a lot. I mean, it's only 24, but I do have particle movement. It's not negative. And is it thermodynamically favored? And there's only one letter you should be looking at. Since my delta G was positive, what does that mean? Okay, definitely not thermodynamically favored in the forward direction. And why? Because it's positive. That's the explanation, ladies and gentlemen. When they're bringing out H and S and G all at once, and they're going to ask you, like literally, I just took an AP question and just changed the equation around. It kind of looks like the one that's in the book too. Is it endo or exo? Why? Disorder, not disorder. Thermodynamically favored or not? That's it. Just say positive, negative, but bring in the why. It's positive because it's endo. It's positive because more disorder. It's positive, so not thermodynamically favored. These are not essays. These are one sentence kind of things. Okay? So easy peasy, little plug and chug. When you're doing standard free energy change, we tabulate these standard free energies. We usually call them delta G, that little F. Remember on the appendix sheet, it says that little F because it just means in that forward reaction, in that formation, forming those products, forward reaction. Standard state, and this is definitely for him. You get a little bit more kind of detailed. Standard states for pure solids, pure liquids, 1 atm gas, 1 molarity, okay, and those delta G's are 0. As we just saw in the appendix, we don't have to look those up. Let's don't waste time, okay, because they're not going to be there. You're not going to have an appendix on the AP test. It's going to be a little data chart. So we can use just like delta H. It's just delta H didn't mention anything about concentration, okay? So you know there must be something about concentration coming, and he is coming. It's in chapter 20 though, okay? That's where it's going to end up, where we're going to end thermodynamics with some electrochem. So be on the lookout, beware when concentration changes. And it's not 1 atm. You don't get that love right now. That crazy can come at the very end. We're going to go products minus reactants, and remember that delta G. Delta G tells us whether it's thermodynamically favored in the forward direction or in the reverse. Okay, so if it is thermodynamically favored, reacts to produce more reactants or products, whether it be positive or negative. Okay, so the delta G for the reaction tells us whether the mixture of a substance will spontaneously, thermodynamically favored, react to produce more reactants. And that means if it produces more reactants, I want you to make sure that you're reading the sentence correctly, because I don't want you to think that the delta G being positive means thermodynamically favored. Notice what it says, producing more reactants. That means it's favored in the reverse direction when that delta G is positive. Or is it thermodynamically favored when it produces more products? And that delta G should be negative. And that means that it's favored in the forward direction. That delta G will be negative. Okay? So let's try one of these little products minus reactants. Okay? So I gave you an equation right here. Use the data from Appendix C to calculate the standard free energy change for the reaction. What is the reverse of this reaction? Which direction is thermodynamically favored? The forward or the reverse? So first, I give you an equation. And let's write down, I usually write my little symbol delta G, okay? So that way I can get some values, okay? Now, remember, standard state. Cl2, I shouldn't even have to look up because right there it's 0, okay? So we know this one is definitely 0. You probably don't know too much about P4. Is P4 actually in the standard state? And remember, AP would be giving you some values. And P4, I believe I had it on there as a gas, okay? Right there, P4 is a solid. P4 is a solid, because remember, phosphorus is a solid. It could be either red or white, is 0. But I said P4 is a gas. So right here, delta G, and I believe delta G is this middle column. Yeah. So right here, P4 is a gas, 24.4. So I'm going to write this on here, 24.4 kJ per mole. And then I have right here, I'm going to be taking 4 times PCl3. And PCl3 as a gas, they said was negative 269.6. Negative 269.6 kJ per mole. And I want to make sure I wrote that down before Lily says I had some dyslexia going on. PCl3 as a gas. And yeah, negative 269.6. Okay. All right. So we have this value for delta G, and then 0, and then this one. Okay. So basically the only one we have to multiply out is this. So we're always going to tell AP that the delta G of my reaction is the sum of all the delta G's for the products minus the sum of the delta G for the reactants. Okay, so my products, we need to multiply that out. So 4 times negative 269.6 is, I'm going to put this right here, negative 1078.4. Now you need to keep that number after the decimal because all you're doing is multiplying by 4. Kilojoules per mole minus this positive number, 24.4 kJ per mole. Okay, and if you don't want to put the parentheses, ladies and gentlemen, you don't have to. Okay, just remember though, you have a negative number minus a positive, so this number is just going to get more negative. So I'm going to subtract this by 24.4, and we still have a number after the decimal, so negative 1102.8 kJ per mole. Okay, so there's my delta G reaction. And what does this tell me? Well, first, what is the delta G for the reverse? Well, if I flip the equation, then my delta G becomes positive. Okay, I know that seems like a very simple question. You're probably thinking like, well, Rodriguez, is there more to it? No, because the reverse is the flip of the equation. So the delta G is a flip of the sign. Okay, same value, just a different sign. Which direction, the forward or the reverse, will be thermodynamically favored? The only one that's going to give me that negative delta G is the forward reaction. So the forward reaction will be thermodynamically favored since the delta G is negative. Period. Done. Okay? Don't overcomplicate this, ladies and gentlemen. It is not difficult. It's just like delta H. Just the only one we probably will have a little bit more practice with, besides products minus reactants, is this one. Because I want to make sure we're not going to screw up the unit.